Hi everyone! Last time we were discussing how to determine if a salt solution is acidic, basic, or neutral. And today we're kind of going to focus more on acids, particularly polyprotic acids. So previously we said that there are some acids that can have multiple hydrogens. So one example is phosphoric acid, which is H3PO4. And if this ionizes in solution, it's going to ionize in steps. So previously we said that strong bases with multiple hydroxide ions will dissociate in one step, but for acids, they're going to ionize in multiple steps. So for instance, we're going to lose one hydrogen ion first, and we'll end up with dihydrogen phosphate. And then we're going to lose a hydrogen from dihydrogen phosphate. And we'll end up with hydrogen phosphate. And then finally, we can lose that last hydrogen on the phosphate, and we'll end up with phosphate. So each of these steps has a Ka value associated with them. So we're going to label them Ka1, Ka2, and Ka3. So phosphoric acid has an acid ionization constant equal to Ka1. Dihydrogen phosphate has an acid ionization constant of Ka2. And then hydrogen phosphate has an acid ionization constant of Ka3. Now, that first loss of hydrogen is actually the easiest loss of hydrogen. So phosphoric acid is going to be more acidic than dihydrogen phosphate, and dihydrogen phosphate will be more acidic than hydrogen phosphate. Oh, that's a 2 minus. So Ka1 will be greater than Ka2, which will be greater than Ka3. And remember, the larger the Ka value, the stronger the acid. Now, phosphoric acid is a weaker acid, so when it loses a hydrogen ion to form dihydrogen phosphate, dihydrogen phosphate can act as a base and grab back onto that hydrogen and reform phosphoric acid. So it is a little bit difficult from that point to lose more hydrogen ions. And that's partly why dihydrogen phosphate is not that strong of an acid. In fact, it's very weak compared to phosphoric acid because it can act as a base. Now, generally, the difference in acid ionization values is great enough that the second ionization does not happen to a large enough extent to affect the pH. A different way of saying that is that first loss of hydrogen is so easy to do that any other losses of hydrogen are going to be negligible and less likely to occur. So for most pH problems, so let's say we were trying to find the pH of this phosphoric acid solution, we're just going to use the first ionization because, again, that first step is going to produce way more hydrogen ions than any of the other following steps. And we'll look at an example later on that highlights that fact. Now, there is one exception to that general rule, and that is sulfuric acid. So sulfuric acid is a really strong acid. So we can actually use the concentration of sulfuric acid as the concentration of hydronium ions for the second step. So when it loses another hydrogen. So that might not make sense right now, but we'll go over it in a second. Your textbook lists some polyprotic acids and their ionization constants. So up at the top, you'll notice we have sulfuric acid, and that is a really strong acid. So its Ka1 value is just listed as strong, and its Ka2 value is 1.2 times 10 to the negative second. Now, sulfuric acid does not have a Ka3 value because it only has 2 hydrogens that it can lose. So we can also call sulfuric acid diprotic because it only has 2 hydrogens. Now, kind of down towards the middle here, we have phosphoric acid. And phosphoric acid, like we saw on the last slide, can lose 3 hydrogens potentially, although it's kind of unlikely. And the 3 Ka values are listed. So you'll notice that we go from 10 to the negative 3 to 10 to the negative 8 to 10 to the negative 13. So those Ka values are decreasing pretty significantly with each loss of hydrogen. And that tells us that the resulting products are much less acidic than the original phosphoric acid. So again, that first loss of hydrogen is really going to determine the pH, and the other losses of hydrogen are not going to have much of an effect on the pH. Now, we can also call phosphoric acid a triprotic acid because it does have 3 hydrogens. And then there's some other acids here. We'll look at an example of ascorbic acid. There's also carbonic acid, which is present in sodas. And there's a few others there as well. So let's look at that exception of sulfuric acid. So again, this is a diprotic acid. So it will lose 1 hydrogen initially in its first step. And in this first step, sulfuric acid is reacting with water to produce hydrogen sulfate and hydronium ions. Now you'll notice that there's just a single direction arrow there. So sulfuric acid is completely ionizing in that first step. And then in the second step, hydrogen sulfate is reacting with water to produce the sulfate ion and a hydronium ion. And then there's a Ka2 value listed next to it. And for step 1, it's just listed as strong. Now, for most sulfuric acid solutions, the second ionization is significant and must be accounted for. So again, this is just for sulfuric acid. Now, because the first ionization step is a complete ionization step, that means that we can say the concentration of H2SO4 is equal to the concentration of hydrogen sulfate, as well as the concentration of hydronium ions. All right, so let's actually calculate the pH of a 0.01 molar solution of sulfuric acid. Okay, so in step 1, again, we had sulfuric acid reacting with water, and it completely ionizes to produce the hydrogen sulfate ion and the hydronium ion. So because the initial concentration of sulfuric acid, oops, I missed the sulfur in there. That's important. Was equal to 0.01, and this is a complete ionization. That tells us that the products will also have that concentration. So this is actually going to carry into the second step. So I'll use a different color for the second step. So again, in the second step, we're starting with a concentration of our reactant that's equal to 0.01. And then we don't know how much of each product we'll end up with. However, we also know that we're already starting with an H3O plus in solution that's equal to 0.01. So whatever this second step produces in terms of hydronium ions will just add to the amount that's already there from the initial step. So the concentration of the hydronium ions at equilibrium, because remember we have two double arrows, or a double arrow here, that's going to equal 0.01 plus whatever we have from the second step. Okay, so let's actually go through the process of figuring out what X is, because we do want to figure out the total amount of hydronium ions for sulfuric acid. Now, just a side note here, this is only for sulfuric acid. Other polyprotic acids, we're only going to consider the first step, not any of the subsequent steps. Okay, so let's set up an ice table for that second step. Okay, and we already said that in the second step, we're starting with 0.01 moles per liter of hydrogen sulfate. And we're also starting with 0.01 moles per liter of hydronium ions. And again, those are coming from step 1. Now, we don't have any of our sulfate ion just yet, but once the reaction gets going, we're going to lose some amount of our reactant, and then we're going to gain that amount in our products. And then for equilibrium, our expressions will be 0.01 minus X for the reactant. For sulfate, it's just X. And for the hydronium ion, it will be 0.01 plus X, like we saw previously. So now the next part, we're going to set Ka2 for sulfuric acid, because this is the second step, equal to the concentration of SO4 2- at equilibrium times the concentration of the hydronium ions at equilibrium, all over the concentration of hydrogen sulfate also at equilibrium. So previously we said that Ka2 was 1.2 times 10 to the negative 2, and that was from the table. So we'll set that equal to x times 0.01 plus x all over 0.01 minus x. All right, so unfortunately here, Ka is too large to make an assumption that x is small. Now, this does make sense because sulfuric acid is a strong acid. So presumably we are going to produce a lot of the product, which means that there will be a significant change. So x, which is our change, will be quite large. So we can't really ignore the change in x for this particular problem. Now, unfortunately, that means we have to use the quadratic formula, which is not my personal favorite, but we can tackle it together here. So we're going to rearrange the equation we have here and set it up in a quadratic form. Okay, so we have 0. Oh, let me rewrite this. Okay, so we have 1.2 times 10 to the negative 2 times 0.01 minus x. And then that's equal to 0.01 plus x times x. Okay. So let's factor some of these things out. So we've got 0.00012 minus 0.012x, and that's equal to 0.01x plus x squared. So then 0 is equal to x squared, and then we're going to add together those two x factors there, so we get 0.022x, and then we just subtract 0.00012. Okay, so we've got our A value, which is 1, our B value, which is 0.022, and then our C value, which is negative 0.00012. So don't forget those negative signs. Okay, so now let's plug everything into the quadratic formula. Oh, not plus, it's minus. See, I don't have you guys here to yell at me when I get stuff wrong. I have to catch my own mistakes. Okay, so we've got our values plugged into the quadratic formula. And if you want to pause the video and try to solve for x, you should get two different answers because we do have a plus or minus sign there. And the two values that I got here were negative 0.027 or 0.0045. Now remember, x is equal to the change that's taking place, and we can't lose a negative amount, so the answer must be this positive value. Okay, so that is equal to X. Oh. So now H3O plus, the concentration of the hydronium ion, we said that at equilibrium it's equal to 0.01 plus X. So that would be 0.01 plus 0.0045. So the total concentration of hydronium ions from both steps of the ionization of sulfuric acid will be 0.0145 moles per liter. So now we can finally calculate the pH of this solution. So we're going to take the negative log of the concentration of hydronium ions, and we should get a value of 1.84. So that does make sense. Sulfuric acid, we know, is a very strong acid, so we should have a pretty low pH. So that does line up. Okay, now remember, this is just for sulfuric acid. Let's look at an example of a regular polyprotic acid. So this is ascorbic acid. So if ascorbic acid reacts with water, initially it loses one hydrogen ion to produce the ascorbate ion and the hydronium ion. And your textbook does walk through an example for how to calculate these concentrations of hydronium ions. Again, it just involves the use of an ice table, and it's very similar to how we've solved the concentrations for other weak acids. But then once we've formed the ascorbate ion, that can react with a water molecule to produce, that's the hydrogen ascorbate, I believe, and then the ascorbate ion has a 2- charge. But then we also produce more hydronium ions. However, if we add together those two hydronium ion concentrations to get the total hydronium ion concentration, we end up with 2.8 times 10 to the negative 3 plus 1.6 times 10 to the negative 12. And then that just equals 2.8 times 10 to the negative 3. So for most polyprotic acids, we can ignore Ka2 and Ka3. The concentration of hydronium ions from step 2 and 3 are negligible. So if you're trying to determine the pH of most polyprotic acids, you can just focus on that first loss of hydrogen. You don't have to calculate the concentration of hydronium ions for any subsequent steps. But as we saw for sulfuric acid, that's not possible. Okay, so the next thing I wanted to go over was how to determine the strength of different binary acids. There are a couple of trends that we can use to determine relative strengths. So Remember that there are two different types of acids. There are binary acids and oxyacids. Binary acids have a hydrogen or one or more hydrogens attached to a nonmetal, typically. And then oxyacids have hydrogens attached to polyatomic ions. So we're going to start with binary acids, and then we'll talk about some trends with oxyacid strength. So for binary acids, in general, the more polarized the bond, the more acidic the acid is. And then the stronger the hydrogen bond to the nonmetal atom, the weaker the acid. So remember, acid strength has to do with how easily a hydrogen ion is donated. So if something can donate a hydrogen ion really easily, that means that it is a very strong acid. But if something does not donate a hydrogen ion very easily, then it is a weak acid. So if we're looking across a row of the periodic table, binary acid strength will increase to the right. So this has to do with the electronegativity of the nonmetal, and therefore it has to do with the polarity of the bond. So if we're looking at a hydrogen that's bonded to carbon, that's a nonpolar bond. So that hydrogen is not going to leave that carbon. It's probably going to stay right there. So if you have a hydrogen bonded to a carbon, it's not very acidic. Now, if you have a hydrogen bonded to nitrogen, hydrogen has an electronegativity value of 2.1. Nitrogen has a value of 3.0. So that is a polar bond. And then if we look at hydrogen and oxygen, that's even more polar. There's a larger difference in electronegativity values. And then if we look at hydrogen and fluorine, that is a very polar bond compared to the other three. So fluorine will be able to give up its hydrogen much more easily due to that extreme polarity. So that means that hydrofluoric acid will be more acidic than water, for instance. So if we're looking on our chart off to the right. So up above you can see that if we have increasing electronegativity, that equals increasing acidity, going left to right. Now, what about going down a column? So if we compare hydrofluoric acid to hydrochloric acid, what's the main difference there? So it has to do with bond strength. And in a previous class, so 162, we talked about atomic size. And atomic size increases going down a column. So if we compare the hydrogen atom, which I'm going to draw as a red atom here, and let's say we compare that to the halogen it's bonded to, the atoms are just getting bigger and bigger and bigger. And remember that as the distance between nuclei increases, that means we have a weaker bond between those atoms. So hydriodic acid can actually give up its hydrogen really easily because it's not very attached to hydrogen. The iodine's very large, and so it doesn't attract hydrogen very well. So hydrogen can just leave, and it doesn't make a huge difference to iodine. So if you do have a weaker bond, that means that you have a stronger acid. So your textbook has this nice table that lists bond energies for hydrofluoric acid, hydrochloric acid, and hydrobromic acid. We already knew that hydrofluoric acid was weak and that hydrochloric acid was strong. And now we know that that has to do with the atomic size of fluorine versus chlorine. Okay, so now for the strengths of oxyacids, oxyacids have the general formula where hydrogen is bonded to oxygen and oxygen is bonded to some other atom. Now, that atom is represented by Y, and Y could be bonded to some other objects or other elements, but in general, oxyacids have this type of formula. So we're going to look at the example of hypochlorous acid and hypoiodic acid. So even though these are written as HClO and HIO, their actual Lewis structures are in a different order. So the hydrogen is actually bonded to the oxygen, and the oxygen is bonded to the chlorine for HClO. And then for hypoiodous acid, it's the same thing, except instead of chlorine, we have iodine. And chlorine has a electronegativity value of 3.0, whereas iodine has an electronegativity value of 2.5. And this is going to have a large effect on the acidity of these molecules. So because chlorine is more electronegative, it's going to really draw electrons away from hydrogen and make it positively charged, whereas iodine is less electronegative, so it's not going to draw electrons away as much as chlorine does. So with that higher electronegativity value on chlorine, that means that the HO bond is weaker. So this acid is stronger. So we can lose that hydrogen much more easily in hypochlorous acid versus hypoiodous acid. Now chlorine does come before iodine if we're going down a column. So the acidity of oxyacids decreases down a group. So this is the same trend as binary acids. Okay, so your textbook has a table of those different types of acids. So these are the oxyacids. And the electronegativity of Y, which are the halogens in this case, are shown. And then you can also see the strength of the acid here. So chlorine is more electronegative than bromine, and bromine is more electronegative than iodine. And so the acids are getting weaker and weaker as the electronegativity is decreasing. Okay, so now for another trend with oxyacids, the more oxygens that are attached to Y, the stronger the oxyacid. So we're going to compare two oxyacids, HClO3 and HClO2, so hypochloric acid and chloric acid and chlorous acid. Getting all my names mixed up. So again, we have that general form where hydrogen is bonded to an oxygen, and then that oxygen is bonded to another atom, Y, and in this case it's chlorine. Now for HClO3, chlorine is also attached to two other oxygens, and for HClO2, chlorine is bonded to only one other oxygen. So the only difference between these two molecules is that extra oxygen. Now, because there are those extra oxygens on the left-hand molecule, that's going to create a larger pull of electrons. So with more oxygens, we're going to further weaken and polarize the hydrogen-oxygen bond. And that means that we have a stronger acid. Okay. And then your textbook has another table showing the trend in the number of oxygens versus acid strength. So you'll notice that as the number of oxygens on chlorine is increasing, the acid strength is increasing. So let's summarize everything we just went over in terms of acid strength for binary acids versus oxyacids. So for binary acids, we saw that the strength of an acid increases going left to right across a row. And then it also increases going down a column. So this is acid strength. And then for oxyacids, there were 2 points, and remember that oxyacids have the form HOY. So the first point was as electronegativity of Y increases, the acidity increases. And then the other point was as the number of oxygens increase on Y, the acidity increases. And again, this really has to do with the bond between hydrogen and oxygen for these different oxyacids. So on a quiz or a test, I would give you reasonable acids to compare. I would either give you 2 binary acids to compare, maybe 3 binary acids, or I would give you 2 or 3 oxyacids to compare. But I'm not going to make you compare binary acids to oxyacids. We would need Ka values for that. So I'm not going to trick you with these trends. But these are trends that you should know. Okay, so we have one more video this week, and it will be on Lewis acids and bases, and that will actually be the end of chapter 16 material. So I'll see you in the next video.